Until this point, we've been talking about lighting, and we've been going into it with trying to understand what a surface normal is, how to define a light direction, and these are all unit vectors, which are vectors of length 1. These are useful tools that we can use to kind of describe our surface. And from there, you can quickly get into more of the kind of reflectance formulas to describe more complicated surfaces. And some of the kind of intimidation factor that can set in is you can encounter some of these and they end up being these really long, complicated formulas. Because a lot of these have very mathematical roots on describing how light moves, which can be fairly complicated to figure out how to actually model that. But when programming, we have these nice variable names, and we can start to break down all of these various complicated formulas to find kind of these simpler names to describe them. And so I'm going to talk about the Blinn Phong lighting model, which is kind of the next step up from Lambert. And most of the time you can get some kind of software to figure this out for you, and you don't have to actually create all these by scratch. But it can come in handy at times to be able to know how to dive into some of them. So this video might be, I might gloss over some details, but just to show you kind of the basic approach of taking a more complicated formula and breaking it down to something simpler and in terms that you can understand. So if you think about a surface, a ray could actually come in and reflect off the surface, creating a specular highlight. And this is kind of nice to be able to do, but in order to do that, you have to know where the light's coming from and where the camera is in relation to that surface. So there's a few more vectors that we need to figure out. And going to the Wikipedia page on this lighting model, you can see we have different terms now. N is the normal vector, the surface normal that we've dealt with before, and L is the lighting. Those are two that we've created before and figured out how to use. The V vector is the view vector, so it's the vector that's going from the surface that points to the eye of the camera of the viewer. And then there's the H vector, which is the halfway point between those, between the lighting and the view normal. And that's just a useful thing to be able to plug and chug into a formula. And finally, there's R, the reflectance vector, which is what we actually care about computing and figuring out. So that would be as if the light hit the surface and then bounced off, doing a reflection. This will help us get the specular color and the kind of interesting shininess that changes according to where our model and camera are. And so I'm going to just skip all the WebGL code and let's look at actually let's go up here to our Vertex Shader first. So our Vertex Shader, we care about a new thing now. We care about the position of the surface in world space. What that means is we take the initial position that's in our data and we apply the model matrix to it only. So that positions it in world space, not in camera space. It's its own like place out there. And we need that for a computation. So there's one additional step of getting that information in the Vertex Shader and passing it down to the fragment. So there's going to be a bit of bookkeeping here as we figure out all the things we need to compute. I have a lot more inputs now. I have the camera position. Again, we have the color of the model that we had before. We even have the color of the specular highlight. So how that light, if that light reflects, does it change color as it reflects? I've added in ambient light to say, is there a base level of light to kind of fake some of the other reflections of light in the world. And then finally, we have two different values, the specular amount, which I'll just go ahead and drag up here, which 0 means no specular highlight, and then a higher one means it's shinier. And then the shininess, which is how kind of tight is that reflection and how spread out is it. So you can see we can adjust those values a little bit here to create different effects. So this is a nice tool to start to be able to describe the surface and play around with it. Then we have here we have a single light we'll go through and apply that using the shading model. and then the two values that we pass down. So that's kind of our bookkeeping. And here, I'm going to start glossing over some things because there's a bit of bookkeeping to figure out how to compute everything, and there's probably good tutorials to get you through this process. But you can see I'm defining a direction to the camera, which is our current position to the camera normalized, so it turns into a vector. Halfway vector. So we take those two and then put them together. Our specular brightness is going to be that component. So if you find the formula and chug everything in, we can put in the specular amount. There's a power function that is taking a dot product. Again, you're going to see lots of dot products doing lighting. And then the shininess factor is how much that's going to go. If you've noticed, these are all variables that you could just put numbers in, but I've hooked them up to uniforms so I have the ability to adjust and play with those values. And now we're going to first calculate the brightness using the Lambertian lighting model, which we covered previously, taking the normal light dot product and surface brightness. And our final function, if we kind of break this out a bit, is, let's go ahead and do this. We're going to take our base color times our surface brightness, so that's our normal Lambertian lighting. But now we're going to add on to it the specular color, the XYZ, times the brightness. So we're just taking one lighting model and then pegging on another. We've glossed over tons of detail here, but it just shows how if you can take an existing formula, compute the vectors you need to do, get them in the right place, you can start to play with those. And once you have those values and you know how to get them in the right place, you can start tweaking them. So you can add sine waves to like what the normal's doing, or like create some kind of disturbances on the surface and do all kinds of different things. So if you can kind of dig a little bit into some of the details and do some further reading about different lighting models and how you can use them, and you don't necessarily need to implement them yourself, you can look them up. Use like GLSLify or 3JS has their shader fragments you can use to be able to do some of the hard work for you, but then get the benefits of being able to hook in your own variable names, feed the data in. I mean, a lot of it's just picturing in your head, I need this piece of information here. How do I get it from wherever my original thing is defined and feed it into the point that I need? And then you can use it kind of expressively draw things on the screen. So yeah, that's the end of me rambling about lighting. The code will be posted below, and yeah, check out some of my other videos and let me know if there's anything that you want me to ramble on about. Hope you enjoyed it.